Now let's do some review that might be helpful when you try to go through the test. One question you're always going to ask is which Planck's constant do you use? Because remember, we have two. One is 6.63 times 10 to the negative 34 joule seconds, and the other is 4.14 times 10 to the negative 15 eV seconds. Now, clearly, it's never none. Well, it might be none. You may not need it. If you're doing E equals mc squared, you won't need one, but it will never be both. When do you use this one? Well, suppose I tell you the energy is 4.3 times 10 to the negative 19 joules. And say I'm looking for the frequency. When I do E equals HF, the H I needs to be in joules because my energy is in joules. Similarly, if I had told you that the energy was 4.3 EVs, all right, then if I'm looking for the frequency, or say I'm looking for the wavelength of E is hc over lambda, then this H right here has got to be in EVs because my energy is in EVs. So I'll use 4.14. Now, wave or particle theory. This confuses a lot of people. Remember, a wave in wave theory explains things like reflection, refraction. Particle theory is when our light waves, act like particles, and so some of this is a little confusing. Okay, clearly interference. Here you see the waves interfering with each other and creating periods of high and low troughs. All right, this is a wave. This can be explained using wave theory. Now, what about the double slit experiment, when we have light of a given wavelength coming in, two slits separated by a distance d, the slits and the screen are separated by a distance l, and then we're having these interference patterns. Let's see, the first one we go to is y here. We're seeing an interference pattern. Do you see I'm using wave words? So double slit is also a wave nature of light. The one that confuses everyone totally is the quantization of electron orbits, ELECTRON. All right, this is actually a wave nature of light. Now think about this. You know I went up and down the ladder, and I could only go up discrete levels of the ladder. But what this is imagine the electron is a wave. I mean, if it's a particle, you can put it on any shelf you want. But if it's a wave, it has to have just the right wavelength and just the right frequency so that it overlaps itself. And remember when we did standing waves, how you had to have just the right frequency for the wave to go down and come back to have that nice standing wave? Imagine instead it did something like this, and we're going to pretend like this is a nice even wave. Do you see how it doesn't meet? All right, if it doesn't meet so that it can't keep going on the same wave pattern, this is not stable. The electron can't be in a stable orbit if it's doing this. It's just going to wind up going off all weird. So it turns out that the quantization of the electrons in orbits is a wave theory as well. Now the photoelectric effect, we've got light coming in as waves, and then it's popping off particles. So this one's pretty clear that this is a particle theory. Now, match the physicist and the theory. Oh, goodness gracious. Double slit. We're going to go backwards. Double slit. This is always Young's double slit. So, we're talking double slit. We're talking about Young's theories. Spontaneous radiation. Now, there were actually two people who did spontaneous radiation. One was Madame Curie and her husband Pierre, and then Becquerel. Particles act like waves. This is when we're finding the de Broglie wavelength. So this is de Broglie. And remember we said H is lambda P. Each wave starts a new wave, more propagating. This is Huygens. And matter and energy are the same. Well, that's Einstein. And the photoelectric effect is also Einstein. You know, this is kind of hard to see. So what I'm going to do is I'm going to clear it. Let's see if I can find my clear button here. All right. I'm going to do them in different colors. How does that sound? What did we find for Einstein? Einstein was matter and energy are the same. Let's see. Madame Curie and Becquerel were spontaneous radiation. Huygens, let's do him in bright yellow. Huygens was the waves. De Broglie was when particles act like waves. And then Young is double slit. That might be easier to see. Now we're going to match the theory and formula. All right, let me go back to the color thing. These get kind of confusing. Energy of a mass. Well, that's E equals mc squared. Actually, I can do highlighters. Let me do highlighters. Energy of mass. This is E equals mc squared. This is a rest mass. And remember, always convert your mass to kilograms. And your energy is always going to be in joules. The photoelectric effect. Let's see, this is the graph we do. This is when the kinetic energy is the energy of the incident light minus the work function. The de Broglie wavelength I just did, let's see. The de Broglie is, where is it? Oh, that the momentum times the de Broglie wavelength has got to equal h. That little h keeps popping up all over the place. And this h will usually have in joules, seconds, because we're going to put the wavelength in meters and the mass in kilograms. Young's double slit experiment. Let's see. The double slit, is d lambda equals Ly. And then the energy of a photon, let's see which one this one is. The energy of a photon is E is hf or hc over lambda. So you need to be able to distinguish between these so you can, when I ask for the energy of a mass, I'm looking for this equation, while if I'm looking for the energy of a photon, I'm going to be using this equation. All right, matching symbols. All right, let's start up here. Half-life. Well, that's T of 1/2. Decay constant is lambda. Now I'm going to pop down here because we also use the same symbol for wavelength. Work function is phi. Work phi. Where's phi? It's down here. Planck's constant, we should just be so familiar with, is h. It's right there. Whenever I look for energy, energy is always capital E. The speed of light is c. Well, some of these got a little lined up. And kinetic energy is always Ke. Kinetic energy is different from energy. All right? Because kinetic energy, let me go to my pen here. Kinetic energy is always going to be Ke. Well, the energy is going to be hf or hc over lambda. And kinetic energy is 1/2 mv squared. So these are actually different, so be careful. Now, half-life is it the time for the radioactive sample to completely decay? No, the word completely is what's wrong here, so it's not correct. The time for half of the radioactive sample to completely decay. I don't know about that. Let's go on to the next one. This one's a little confusing because of the word completely. Time for half of the radioactive sample to decay. Okay, this is the definition I've been giving you guys. At half of the life of the radioactive sample before it decays. Okay, that doesn't make any sense, does it? Half of the life of the sample. Well, no, that's not right. So, I've been giving you this one. Could it be this one? Time for half of the radioactive sample to completely decay. You know, I wouldn't put this one because this word completely kind of confuses me. I would select time for half of the radioactive sample to decay. It does completely decay, but we haven't discussed what that might mean in a radioactive sample. Quantum mechanics. Quantum's just cool. Okay, if I put E, quantum mechanics is cool. Okay, you kind of have to check that one. All right, quantum mechanics is when we consider light as both a wave and a particle. I'm going to put E down here, or 5, cool, because it is just the wildest subject. Now, does it absorb or eject? Okay, now you see here I have energy coming in, E equals HF is coming in, and it's taking the electron, this is my electron, and it's putting it in a higher orbit. Now you remember when I climbed the ladder, as I absorbed a photon, I went into a higher orbit. So this is absorb. Now here I've got my electron and it's shooting off a photon. This one's kind of obvious. It's ejecting the photon, isn't it? It goes from the higher orbit down to the ground state. So this is obviously eject. Now, does the energy increase or decrease? All right, let's look, and we're talking about the energy of my electron. My electron is here, and it's very happy. Photon comes in, and it gets absorbed. So just like eating a bag of potato chips, you're going to increase your energy. So here, my electron increases in energy. While down here, it's losing energy to this photon. This photon has energy HF, and it's lost it. So here it's going to, I'm going to say lose, but also decrease energy. How can you tell if something's radioactive? Well, if a particle comes from radioactive decay, it is probably radioactive. It might not be. I mean, you might have a proton, you might have a neutron. But it is probably, not always, it's probably radioactive. Now, if it's warm or hot due to decay, this is definite. This is definitely how you can tell something is, probably radioactive. And I'm going to say probably because, I mean, I know one of you is going to say, but what if I just pull it out of the oven? All right, it's lying on the ground, sitting in my desk, and it's hot. And it's been there overnight. It's probably radioactive. So don't touch anything on my desk. That's the clue there. Glows in the dark. All right, well, remember the story of Madame Curie, where she noticed a beautiful blue glow coming from the test tube of thorium. Well, yeah, if it glows in the dark, chances are it's radioactive. Get cancer if you're exposed to it. Probably, basically it's not one-to-one here, but if it's radioactive and you're exposed to it, the chances are you're going to get cancer. That's what the radioactivity does. It goes in and it dinks your cells, and it causes them, it changes them. And so basically any of these can be an indication of radioactivity. I guess the most valid way to determine is to use a Geiger counter, is to measure the activity. And if it pings, then it is radioactive. Now, fusion. Fusion, think about this. Fusion is when you take two small atoms and push them together, and that releases energy. Oh, isn't that a lovely picture? It looks like some weird guy with strange hair and eyeglasses. Okay, so fusion, what does this also look like? This also looks like the sun, all right? Anytime we say fusion, think sun. S-U-N, fusion, sun. All right, is it two heavy nuclei come together? No, it's never heavy. Fusion is always light. Large, unstable nucleus breaks into two or more parts. No, fusion's when you're shoving them together. So anything with two or more parts I'm going to put out. Two light nuclei pushed together, releasing energy. Here's your answer. It will release energy. Fission is when you have this large, unstable, and it tends to want to break off. And this is, remember, this is very dirty. This gives a lot of very toxic products, you want to be very careful when you have fission. Okay, so it's not when two heavy nuclei come together. It is when you have a large unstable nucleus, breaks into two or more parts, is not too light. Well, no, that one doesn't make any sense either. It's not too light. It's too heavy. Now, which of these do we get bombs from? Fission, fusion, both, or neither? And yes, I know. When I put neither, don't get confused about where it is. I mean either of these two. Well, the answer is both. You have both atomic bombs, fission bombs and fusion bombs. Now, draw and completely identify the parts of a Ke versus F graph of the photoelectric effect. All right, first thing I'm going to do is cheat and bring in, I have a nice little graph here. So I've drawn it. Now, you have to label it. This is the kinetic energy. This is the frequency. And then you're going to have this line. And you remember the slope of the line is always Planck's constant. This point right here, it's a frequency, and this is my cutoff frequency. So F naught is cut off. Cut. C-U-T. Oh, do you ever have days when you can't spell? Cut off. Frequency. And it's a frequency when, do you see if I read this, my kinetic energy is 0. Ke equals 0. This point right here, my y-intercept, where it intersects the y-axis, is minus 5, where this is a work function. And it's negative because the work function is always going to be positive. So this is a work function. All right, now, what is the equation of a line? Y equals mx plus b. The y in this case is kinetic energy. The slope, m, is h. X is my frequency. And b is minus phi. So this is the photoelectric effect formula. And this is the labeled value of the kinetic energy versus frequency graph. Now, folks, could I be mean to you and have you read off a point? Of course I could. All right? Be able to read a graph. Now, this one down here is draw and completely identify the parts of an N versus T graph for radioactive half-life. Now, this has been sitting on my board. Don't you just love how I can just pull these in? You can't. All right, here's the trick. This is N. This is what you start with. N. This is a total number that you have at any time. So a lot of times this point right here is N naught. This is a number you start with. And then just draw this curve going down. All right. Now, halfway down, because this is 0, halfway down, this is 1 half-life. Whoops. This is 1 half-life. And so, well, do you ever just... So this is when N is 1/2 of N naught. So draw your line. And this time right here is T of 1/2. When you cut this in half again, this is 1/4 N naught. And this is 2 half-lives. I'm running out of room, so I'm going to circle it up here. 2 times 1/2. Cut it in half again. This is 1/4. Okay, this is 1/8 N naught. I can't write very well, so I'm not going to try it. And so this is 3 half-lives. So don't worry too much about the formula. N, the number at any time, is however many you start with, e to the minus lambda t. But do be able to read off a graph or draw a graph to show the half-lives. Now let's look at the energy absorbed by photons. Okay, absorbing, let's just go up. It's the same as the energy emitted. To go from n equals 1 to n equals 2, let's see. I'm always going to talk about a change in energy, say from end to end. And basically, what we're going to do is we're going to subtract. So this is going to be E2 minus E1. So to go from 1 to 2, and I'm going to come over here, and E2 is 10.2. All right, and I'm going to subtract 1, which is 0, so it's 10.2. All right, the energy to go from 1 to 3 is 12.029 minus 0. 12.09 minus 0, or 12.09 EVs. And this is all EVs. Okay, so it's very clear how to go from 1 to 2, 1 to 3. I mean, you can do 1 to 4. All right. You kind of have the idea. Oh, I lost my pen here. You kind of have an idea how these work. Come on, pen. 1 to 4, 1 to 5. These are all going to actually wind up being this value. Infinity, of course, is when you get it completely away from the atom. Now, suppose we go from n equal 5 to n equals 6. How would I do that one? All right, you ready to be shocked? It's just 13.6 minus 13.06. Handy dandy calculator, that's going to be 4. This is going to be 0.54 EVs. Kind of got the idea. To go from 3 to 4, all right, it's going to be 12.75 minus 12.09. You have the idea. Whichever one you start with and go to, just subtract those two numbers. And once you've done that, you can find the energy. Once I have the delta E, so let me come up here. E, or the change in energy, is HF. Once I find delta E, I can find the frequency. The frequency is going to be delta E divided by H. Now, remember, which H are you going to use? The 4.14 times 10 to the negative 15 EVs. All right, so for these, use H is 4.14 times 10 to the negative 15 EV seconds. Okay, got to use one with EVs for this. I might ask you for the wavelength, in which case E is hc over lambda. Solve this for lambda, it's hc divided by E. You can do these. Now finally, be able to convert from meters to nanometers, or from nanometers to meters. Remember, everything in our problems usually has to go into meters. Be able to analyze the photoelectric effect problems. You need to be able to find the threshold wavelength and or the threshold frequency. Now what does that mean? That means your kinetic energy is going to be 0. So if I'm looking for frequency, I'll just solve this equation here. HF minus phi. So F is phi over H. But if I want wavelength, I have to remember that I can also write this as hc over lambda. So 0, I lost my pen, sorry about that. 0 is hc over lambda minus phi. Solve this for lambda. Lambda is going to be phi over hc. All right? Find the kinetic energy given the work function and the frequency or the wavelength. Again, that will just be plugging straight into this equation right here. E equals mc squared. Okay. If I will give you a mass in kilograms. C is 3 times 10 to the 8th. The big trick here is make sure you do c squared is 9 times 10 to the 16. For the fraction gratings, this is make sure everything is in meters to start with. Lambda is the wavelength of light. L is the distance from the slits to the screen. And remember, L is going to be your big number. D is the distance between the slits. And Y is the distance up to your first maximum. Energy diagrams, be able to calculate those energies. Okay, this is going to be the energy from 3 to 4 is going to be the energy at 3 minus the energy at 4. We just did that. And find F, or find the wavelength. I just showed you how to do this. For radioactivity, you're going to have to find the half-life or the decay constant. Well, you remember the half-life is 0.693 divided by lambda. So if I give you the decay constant, you can find the half-life. If I give you the half-life, you just switch this around, and you can find the decay constant. And then how much radioactive material is left after a time t. So you can do this. Study. This is your last test of the semester, of the year, before the final. The last of your new material. Y'all are in great shape.